Please wait. Good morning, everyone.
Good morning, ma'am.
So today we'll continue with transformer that I have started already. Let me share the screen. The screen is visible to you, right?
Yes, ma'am.
Okay. Okay. So I was discussing ideal transformer operation. Transformer works on the Faraday's laws of electromagnetic induction. That means wherever there is a change of current or change of alternating flux in a coil, an EMF will be induced by electromagnetic induction following the relationship E equals to n d phi dt that we have seen already. And here is the basic block diagram of a single phase transformer. You can see the two windings wrapped around the same core, which contains the mutual flux phi m, and this phi m generates because of the alternating voltage Vt and the alternating current Ip, which is flowing through the primary coil. So whenever there is an alternating current or alternating voltage through a coil, an EMF will be induced, and that EMF will further develop a secondary induced EMF across another coil, which actually uh, links with the same flux, right? And this secondary side is connected with a load. So once the load is connected, what will happen? Secondary current will be flowing. So here, this is the relationship EP by ES equals to NP by NS. This is the voltage relationship for ideal transformer. Ideal transformer means a lossless transformer, loss-free transformer. Considering that there are no losses. In transformer, losses can be of mainly two types, core loss and copper loss. Core loss mainly generates inside the core, right? That can be of two types again, the eddy current loss and hysteresis loss. So these two losses, eddy current loss and hysteresis loss, these two losses are related with the core material, the magnetic material, the magnets used to form the core material. This is the core. This rectangular shape uh, drawn in this figure around which the windings are wrapped is the core, right? So depending upon the core material, the losses will vary. The core losses will vary. And other than core loss, there are copper losses. Copper losses means the I square or losses. They are also called as ohmic losses. That means if these windings are having any impurities within it, any internal resistance within it, right? Then that will create I square or R loss. So these are coils. These primary and secondary windings are basically coils, inductances, right? And these should be ideal inductances. There should not be any impurities, any internal resistances. So if there are internal resistances, then what will happen? There will be a drop in the windings. Those are called ohmic drop. And based on these drops, the ohmic losses will be generated. Those are called as copper losses because mainly these windings are made of coppers. Fine. So in ideal transformer, these losses are totally absent. The windings serve purely inductance, right? And with the pure sinusoidal voltage signal at the input side of the ideal transformer, we have seen already this is the EMF equation at the primary side and secondary side respectively, 4.44 NPF of 5 max. How to obtain this equation? How to obtain it? This is based on the Lenge's law and Faraday's law. Uh, Let me write the basic equation. EP dashed is equals to, by applying Lenge's law, it will be minus NP ddt of the mutual flux, right? Now, this mutual flux is definitely alternating in nature because this is generated because of this alternating voltage as well as the alternating current. So, let phi m be 5 max sine omega t. Okay, so what is actually EP dashed? It is minus NP again ddt of 5 max sine omega t is what? Is what?
Omega cos omega t.
Omega cos omega t, right? Uh, Omega cos omega t, and this omega is 2 pi f.
Ma'am, 5 max will be also there.
Yes, I'm so sorry. Phi max is the constant term. It's phi max sine omega t. So phi max is the constant term. So it is np 2 np into pi f phi max into cos omega t, right? So it's 2 pi f np into phi max into cos omega t, or it can be further written as sine of omega t minus pi by 2, or sine of omega t plus pi by 2, right? And now EP dash RMS, this factor actually, this is the constant, this NP F max, this constant is actually E max, EP max, the maximum value, the peak value of the voltage signal. So if you take the RMS value, if you divide that maximum value by root 2, you will get the RMS value. So this is the expression of RMS value of the voltage at the primary side, that is 4.44 NP into frequency into 5 max, the maximum value, right? The maximum value will be obtained when the sine of omega t minus pi by 2 term is equal to 1. The maximum value, right, will be obtained when omega t is equals to pi by 2, depending upon the sinusoidal nature of the signal. The maximum value or the peak value is obtained at omega t equals to pi by 2 or 90 degree. Okay, so from that we'll get the RMS value EP dashed equals to 4.44, because calculate this 2 pi divided by root 2 is how much? This constant 2 into pi divided by root 2, how much?
4.4428.
Yes, 4.442. 442. I'm writing over here EP dashed RMS is 4.44 into F into 5 max into, I'm writing it as sine of omega t minus pi by 2. That is also cos. Okay, similarly at the secondary side, this can be generated 4.44 into Ns, the secondary number of turns into flux into the same mutual flux, phi max. Fine. So this is basically the RMS value of the maximum voltage, the peak voltage at the secondary side. And this is the EMF equation of the transformer at the primary side. Because this relationship, this EMF equation will be required for the analysis of the phasor diagram. That I'll explain later on. So next, move on to the assumptions or the features of the ideal transformer operation. Let us see what are the important features. First is all the flux produced in the primary coil links to the secondary coil. That means there should not be any leakage flux as well. Entire flux which is produced because of this alternating current here at the primary side must be fully linked with the secondary coil. So there should not be any flux leakage. That is one of the most important feature of ideal transformer. Next, no core losses due to hysteresis or eddy currents. No power losses because no ohmic losses are acceptable. And no saturation, no magnetizing phi. We'll see the effect of this saturation and magnetizing phi when we'll study the phasor diagram as well as the open circuit characteristic curve, the BH characteristic curve. Because always in case of ideal transformer, the permeability is kept as infinity, as high as possible. And windings have zero resistance, that we need to assume. That means definitely ideal transformer means windings must be lossless. There should not be any internal resistance in the windings. And the last point is no current required to magnetize the iron core. Actually, in practice, in real transformers, there should be always some current to be flown to the primary winding so that the core can be magnetized always. In reality, in practice, the core should not be demagnetized. Okay, so in order to magnetize the core always, the primary winding must draw some current, maybe a very small fraction of current, 2 to 5% of the rated current, whenever there is no load at the secondary side, right? But still, the primary winding must draw some current from the alternating voltage supply in order to magnetize the core. But it's not required. That no load current is not required in case of ideal transformer operation. So in ideal transformer, the turns ratio is defined by this relationship NP by NS, the number of primary turns divided by the number of secondary turns, or the ratio of the primary voltage divided by the secondary voltage, A, small a. Sometimes it is also denoted as small n. A is the turns ratio of the transformer, very important factor in transformer. Because based on this ratio, this factor, many other parameters are to be studied. So if A, the turns ratio, which is also known as voltage ratio, which is equals to EP by ES, then the primary winding voltage, as I said just now, many other parameters are dependent on this ratio. So this primary voltage EP is nothing but equal to Turns ratio times the secondary voltage. That is the most important EMF equation of ideal transformer. And as I said already, that in transformer working, there should not be any change in power level. Only voltage or current can be stepped up or stepped down, keeping the total input power exactly equal to the total output power at the secondary side, right? So EP times IP, the total volt ampere at the primary side, must be balanced by the total ampere turns at the uh, secondary side, right? So power must be balanced at both the sides of the transformer. So SP must be equals to SS. The primary winding power must be exactly equal to the secondary winding power. And what is the current ratio? Current ratio is definitely the ratio of the two winding currents, that is ratio of IP and IS. IP is the primary winding current and IS is the secondary winding current, and it is exactly proportional to 1 by A. That means the ratio of the two winding currents is indirectly proportional to turns ratio. Okay, that means IP is equals to 1 by A times IS, where EP is equals to directly A times ES. So current ratio is just inverse of the voltage ratio. Next, impedances reflected through the ideal transformers. Z in is the load impedance as seen from the primary side of the transformer, which is just equals to EP by IP after applying the Ohm's law. And what is Z load? Z load is just equal to ES by IS, secondary winding voltage by secondary winding current. Okay, so ES by IS can be further expressed by this EP by IP into 1 by A square. See, I have just considered ES equals to EP by A, EP by A, which is equals to ES, because EP by ES is small a. So simplifying that and considering IS equals to A times IP from the current ratio, we'll get ES by IS, the Z load, as seen from the primary side. As seen from the primary side is 1 by A square, 1 by square of the turns ratio times EP by IP. That is Z in. That means it is just 1 by square of turns ratio uh, into Z in. Or we can say that Z in is equals to A square Z load. That means load impedance is increased when viewed from primary side. And this is reversed if you uh, see from the secondary side, right? If it is viewed from the secondary side, then this relationship will be changed. So it's very much important. It's very much important to understand that from which terminal you are trying to view the impedance of the circuit. See, in this case, it is just reverse. Z load is now equal to A square times Z in. So it is very simple. Look at the figure. Here, this is a Z in. When primary values in terms of secondary and secondary values, and considering EP equals to A times CS and IP equals to IS by A, you can evaluate Z load as this, Z in time A squares. So the circuit characteristics, the circuit behavior can be changed based on these turns ratio and the load impedance and the input impedance of the transformer circuit. Okay, we'll solve numericals later on. Next, coming to the non-ideal operation. Non-ideal operation means real transformer, the practical transformers. As I said earlier, that practical transformers draw current even no load is connected across the secondary winding. Right. So in that case, in case of non-ideal operation, these two losses will be generated. These are active power losses. One is eddy currents and second one is hysteresis losses. So hysteresis losses mainly generate due to the repeated change in the magnetic polarity, and eddy currents will be generated because of the core material. It is generated inside the iron core because of the changing magnetic field, and due to this eddy currents, due to this current generated in the core, eddy current losses also generated in the core. So these two are active power losses in non-ideal transformer, and the transformer core needs to be magnetized always. So transformer primary current must draw some current from the supply at no load condition also. And how to control these two losses? Hysteresis losses can be controlled by using alloy steels for magnetic circuits, and eddy currents can be controlled if you use the laminated core, if you use lamination insulation after the lamination. Okay, if you provide the insulated lamination, then it can be controlled. Now, next, coming to the definition of permeability, because permeability is to be determined in case of magnetic circuit, because a finite amount of current is necessary always to drive the mutual flux between the two coils. A finite amount of current is required to drive the mutual flux confined within the core always, so that it cannot be demagnetized. So permeability is finite, so reluctance is also finite. Reluctance, which is a ratio of L by mu A. Okay, there. R here, reluctance is denoted as R. Pi m is the mutual flux, which is just the total ampere turns divided by the reluctance. So the inductance can be further represented by this relationship, n square by the reluctance. Mu is the permeability, A is the cross-sectional area of the conductor or the coil, and L be the length of the coil. Okay. Now this is the no load circuit model. But before going to this, let me first tell you the phasor diagram of the ideal transformer. Phasor diagram of ideal transformer, and that uh, will be better understood from the EMF equation. Okay, please wait. Otherwise, you will not understand the phasor diagram of practical transformer under no load condition. Okay. phi m, the mutual flux will be taken as the reference vector in case of transformer phasor diagram always. Now, coming to EP and ES, EP and ES, right? What is phi m? Phi m is phi max sine omega t. It's a sinusoidal signal. And we have seen the expression of the primary induced voltage, right? It is just ddt of phi. That means it's a cosine. It's a cosine, a signal. And what is the phase difference? If you represent this EP, you will get sine of omega t minus phi by 2, right? So if phi max is mutual flux is phi max sine omega t, and EP, the primary induced voltage is E max, let it be E max into cos omega t, right? And what is E max? E max is twice n times pi into f into phi m, right? This constant term is E max actually. Is it clear to everyone? E max, what is E max? E max is the maximum voltage. It is just 2n into pi into f into phi m. This is your E max. And negative sign indicates that this EMF induced at the primary site will oppose the very cause of it by Lenge's law. Is it clear to everyone? Do you have any doubts in this issue?
No, ma'am.
Okay, because it is very much important to understand, otherwise you will not get the phasor diagram. So it is clear to everyone that EP is equals to E max into cosine omega t, right? That means your voltage signal is a cosine signal. Okay, that means what will be the direction? Can you tell me the direction of the primary voltage EMF? How it should be placed in the phasor diagram if phi m is the reference one? Flux is the sinusoidal signal and EMF is the cosine signal. What is the amount of phase difference between the two?
Opposite of flux.
No, not opposite of flux. What is the phase difference between these two signals? The flux signal, which is definitely alternating time, and the EMF signal.
Pi by 2.
Pi by 2.
Yes,
Pi by
pi by 2. Absolutely right. Pi by 2. Then in the phasor diagram, how the phasor of the EMF at primary side of the transformer to be drawn? Tell me whether it will be lagging or leading by the flux signal.
Lagging.
Yes, the EMF, the induced EMF at the primary side will be lagging by the flux. Will be lagging by the flux because cosine cos omega t can be further represented as sine of omega t minus pi by 2. Fine. So
Yes, ma'am.
let me draw the signal first. The vector for the voltage signal EP. The primary induced EMF. EP is primary induced EMF. And what is VT? VT is the supplied voltage. AC supplied voltage. This is the supplied voltage. And this negative sign indicates that the induced EMF EP will be opposing the cause, the production of it, that is VT. VT will always oppose EP and vice versa. The primary induced EMF will always oppose the supply voltage VT by Lenge's law. So Vt will be always, where is my cursor? Vt will be always out of phase with Ep, because if Ep plus Ep is 90-degree lagging by the flux signal phi m, flux vector phi m, then minus of Ep, this signal minus of Ep should be 90-degree leading by the flux vector phi m, right? And Vt is nothing but equal to minus of Ep in case of ideal transformer if there are no losses. This Vt is just equal to minus of Ep. Is it clear to everyone? And if there are some resistances in the windings, which is really present in case of non-ideal transformer, in case of real transformer, then depending upon the winding resistance, say Ra, IPRA voltage drop will be there. So in that case, Vt will be minus of Ip plus the voltage drop, say Ip Ra. That means Vt minus the drop is equals to the EMF induced at the primary side, right? This is the equation in case of non-ideal transformer, but this voltage drop is not present here. This drop, this winding drop, this ohmic drop is not present here. So Vt is just equals to minus of Ep in case of ideal transformer, right? So Ep, the EMF induced at the primary side is just 90-degree lagging by the vector phi m. And what is the direction of Es? Es is the induced EMF. Es or E prime S, Es prime, whatever it is. So direction of Es will be also similar to the direction of Ep. That means both the vectors, both the phasors, secondary induced EMF and primary induced EMF, they are in phase. Is it clear to everyone? Because look at the EMF equation, Es, E secondary is also equal to E max of cosine omega t. E max of cosine omega t, right?
Yes,
All of you, please mute your microphone. All of you, mute your microphone. Okay. So Es is also lagging by the flux by 90-degree. So Es and Ep both are in same phase, right? And in case of ideal transformer, basically the number of turns NP times IP, that means total ampere turns at the primary side will be compensated, will be totally compensated by the secondary number of turns. Suppose this is the secondary current Is and this is the primary current IP. In case of ideal transformer, no magnetizing current is required. We'll see the effect of magnetizing current as well as the effect of magnetic flux in the phasor diagram of transformer with loaded condition, right? But here in case of ideal transformer, IP is the primary current phasor and Is is the secondary current phasor. Considering inductive load, considering lagging type power factor, here always Is the secondary current will be lagging by the secondary voltage, right? So this is the power factor angle. This is secondary current. Secondary current is lagging by the secondary voltage. When the secondary current will be generated, when the secondary side is connected with a load, right? So in case of ideal transformer, if secondary side is connected with a load, definitely the secondary current will be flowing. And if the load is inductive type, if the load is lagging power factor type, definitely Is, the current flowing through the load will be lagging by the load voltage. Clear? Will be lagging by the load voltage. Say the load voltage is Vs here. The load voltage is Vs. Es is the EMF induced at the secondary winding. And what is Vs? Vs is the voltage developed at the load side. which is just the product of IS and the load impedance. Z load. IS times Z load is equal to VS, the terminal voltage across the load. And this load voltage will be equals to this EMF induced ES, because there is no resistance in between these two. The secondary winding is purely inductive. No impurity is there. It's a totally ideal transformer. So no losses will be generated here at the secondary side. So the total induced voltage must be impressed fully across the load. So ES is equals to VS. That means phasor of VS will be also in phase with EP and ES as well, right? So you can see this is your primary voltage phasor and this VS is the secondary voltage phasor. They are exactly 180 out of phase by each other. Can you see this? The relationship between VS and VT. VS is just making an angle of 180 degree by the vector VT. VT is the input voltage, input AC voltage, and VS is the output AC voltage. So for ideal transformer, there is exactly 180 degree between these two, which is not possible in real transformer, in practical transformer. Okay. Now, if this is VS, and if the load is lagging type, then definitely IS will be lagging by this VS. Right? Right? And since this is ideal transformer, the total ampere turns at the secondary side, that is NS times IS. If you multiply this secondary current vector with NS, the secondary number of turns, you will get NPIP. You will get NPIP. Okay? The primary current multiplied by the primary number of turns. See, the angular difference is exactly 180 between two. That means total secondary ampere turns must be fully compensated by the total primary ampere turns. Is it clear to everyone? Or shall I draw the phasor diagram once again? Let me draw it. If you have any doubts, any question, please raise your hand. I'm drawing the phasor diagram of ideal transformer. And here magnitudes are definitely same. The magnitude of VP, EP must be same. The magnitude of EP, ES, VS must be same. The magnitude of IP, NP should be equal to IS, NS. Now, is it clear to everyone? Tell me if you have any doubts. So all of you have understood this phasor diagram? So always remember the relationships between phi E, IP, IS, VP, EP, etc. Next, coming to the phasor diagram of non-ideal transformer during no load condition. During no load condition means what? The secondary side is not connected with any load. Though in case of transformer operation, it is always recommended to not to open the secondary terminals, right? It is desired that secondary side is always connected with some load, because if you leave the secondary side open, then there may be some hazardous effect. When the supply is connected with the primary side and secondary side is left open, then huge amount of voltage can be generated at the secondary terminal, at the secondary winding, right? Because the transformer operation is going on. The core is magnetized. The supply is still on. So primary current is flowing. So EMF will be induced at the primary winding, right? And this EMF induced at the primary will develop more EMF at the secondary winding. And imagine the secondary side is not connected to any load. Then what will happen? That huge amount of voltage that is generated, that is developed at the secondary winding, will be impressed fully across the open circuited terminals. So if any personnel or any other equipments are associated with that site, definitely there will be a damage of that instruments or personnel. Okay, so it is always recommended to not open the secondary site. It is always recommended to connect the secondary site with either a load or any device which is having a finite amount of resistance, say an ammeter, right? Ideally, ammeter has infinite resistance. So in case of practical ammeter, there will be definitely high amount of resistance. So if no load is connected, you can connect an ammeter at least across the secondary winding, so that it can be connected with something. Okay. So this is the case at the primary site of the transformer, of the non-ideal transformer during no load condition. So this is the no load circuit model, or the equivalent circuit of the transformer. So you can see here Vt is the primary voltage, the input AC voltage, and this I0 is the exciting current, or the primary current at no load operation, which is also called as no load current. And this no load current is divided into two parts in real transformer. One is called IFE and one is called IM. See, IM is flowing through coil. This IM is actually flowing through the winding or through the coil, which helps to magnetize the core. So this is called the magnetizing current, right? And this XM is the magnetizing reactance of the winding. And this component, IFE, which is actually flowing through the resistance. Through the resistance. What is this resistance? This resistance is just the impurity, the resistance present in the winding, the primary winding. Okay, so not in the primary winding exactly. It is present in this coil. If this resistance is the impurity, then definitely another portion of current will be flowing through this resistance, just to implement the idea that any ohmic loss, if any ohmic loss or any resistive loss is there, then that will be generated because of this current. So no load current I0 will be divided into two parts during the no load operation of the real transformer. Now look at this phasor diagram. Look at this phasor diagram here. This is your phi, the reference vector. This is your phi. And to magnetize the core, or to maintain this phi always within the core circuit, a magnetizing current is required. So Im is associated with this phi, and it will be in phase with phi. Im, the magnetizing current, will be always in phase with phi, because Im is the responsible factor for the magnetization of the core always. Because if the core is not magnetized always, then there will be a fluctuating nature of the flux phi, the mutual flux phi within the core, which is not desirable. The flux should remain constant throughout the operation of the transformer. If there is any variation of the flux, there will be change in the voltage induced at the secondary side, which in turn cause a problem across the load voltage. Right? And what is this IFE? See, this IFE, this component, this current component will be just perpendicular with this flux. Right? Because this is the current which is producing the loss, the ohmic loss, I square into RFE. And the resultant current is I0, which is called the no load current, this current I0, which is the resultant of these two current. So this Im, this current Im is very, very large compared to this. Considering this loss is very, very small, so we'll consider this current IFE to be very, very small compared to this Im. Okay? So these angle must be very, very small. This angle. So in practice, we should assume that this vector I naught is in phase, is almost in phase with this vector phi. Because if this angle becomes 0, then only this practical transformer will act like a ideal transformer. That means if we can make this vector I0 in phase with this phi, then we can conclude that transformer has very, very small loss. It behaves like a ideal transformer, that we can say. And what is this Vt? That is the primary voltage, this voltage, which is always 90 degree lagging by the flux vector. Because this is the EP, the primary induced vector, which is just which is lagging by this flux vector by 90 and just 180 out of phase with the primary voltage Vt by Lentz's law. Now, if you have any doubts, you can raise your hand, because today time is over. We should stop here. So I'll again start from this phasor diagram in the next class. So if you have any queries, students, please raise your hand. If you have any doubts in this phasor diagram or anything from transformer. Are you there?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
What? Yes, ma'am. You have doubt or you have all understood? Or you are in the class, you are present, you are active. Okay. Please wait. Let me give you the attendance. Roll 1,
Present, ma'am.
2,
Present, ma'am.
3,
Present, ma'am.
4,
Present, ma'am.
5,
Present, ma'am.
6, 7,
Present, ma'am.
8,
Present, ma'am.
9,
Present, ma'am.
10,
Present, ma'am.
11,
Present, ma'am.
12, 13, 13, Abhirup. Are you there? Satyam, Abhirup, both are absent. Next, 14,
Present, ma'am.
15,
Present, ma'am.
16,
Yes, ma'am.
17,
Yes, ma'am.
18,
Present, please, ma'am.
19,
Present, ma'am.
20,
Present, ma'am.
21,
Present, ma'am.
22,
Present, ma'am.
23,
Yes, ma'am.
24,
Present, ma'am.
25, Aditya, 26,
Present, ma'am.
27, Aman, 28,
Present, ma'am.
29,
Yes, ma'am.
30,
Present, ma'am.
31,
Yes, ma'am.
32,
Present, ma'am.
33,
Present, ma'am.
34,
Present, ma'am.
35,
Yes, ma'am.
36,
Present, ma'am.
37,
Present, ma'am.
38,
Present, ma'am.
39,
Present, ma'am.
40,
Present, ma'am.
41,
Present, ma'am.
42,
Present, ma'am.
43,
Present, ma'am.
44,
Present, ma'am.
45,
Present, ma'am.
46, 47,
Present, ma'am.
48,
Present, ma'am.
49,
Present, ma'am.
50,
Yes, ma'am.
51,
Present, ma'am.
52,
Present, ma'am.
53,
Present, ma'am.
54,
Present, ma'am.
55.
Present, ma'am.
Okay.
Ma'am, 27.
27. Okay. Next. Aditya Ghosh, Obhirup Sattam, Riddhi. Riddhi, are you there? Riddhi Banerjee. Okay. Thank you, students.
Thank you,
Thank
ma'am.
you, ma'am.
All the best for your internal examination.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
I'll send the question paper through your Google Classroom. Okay. So I hope all of you are in the Google Classroom of this basic electrical theory.
Yes, ma'am.
Okay.
Yes, ma'am.
Did you get the schedule
Yes, ma'am.
of your basic
Yes,
electrical?
ma'am.
Yes, ma'am.
Yes, ma'am.
7th
On Friday.
on 7th
Yes.
7th
Yes, ma'am.
at 10 a.m.
Yes, ma'am.
So at 10 a.m.
Yes,
I'll
ma'am.
send the question paper to your Google Classroom of basic electrical theory, and you will submit the answer script in the classroom only
Ma'am, we have to submit within 11.
within 11. Okay, and definitely at the top of your answer script, you should write your name, roll number, subject name, subject code. Both are given, will be given in the question paper, and date of the exam. Okay, and after that,
Okay.
you
Yes,
will
ma'am.
start writing.
Ma'am, A4 size papers.
Plain A4 size plain paper. If A4 size paper is not available, then only plain sheet, plain paper. Okay, so extra 10 minutes. Actually, it's a 50-minute exam, and after that exam, another 10 minutes will be given for uploading the answer script. And you need to give a suitable file name. I'll mention in the instruction section what you should consider as the PDF file name of your answer script. Okay, so you will read the
Yes, ma'am.
instructions carefully, then you will submit the answer script.
Oh, okay, ma'am.
Okay, and
Okay.
if you feel any problems, any issues during the examination time, you should inform me. Okay, during that interval only, because after
Ma'am,
no answer
ma'am,
scripts will be
sometimes it takes a bit
considered for
time.
evaluation. Yes.
Ma'am, sometimes it takes a bit of time to make PDF. Can I upload the image then if I can't make the PDF?
No, actually, PDF is acceptable file. If not possible, then you can send. First, you should try to send the PDF.
Yes, ma'am, I'll try.
Fail to do, then you can submit the image file. Okay, but after 11, no answer scripts will be considered for evaluation. Be careful
Yes,
about
ma'am.
that. It's a 50 minutes exam, not 1 hour exam. So extra 10 minutes is given there to do this.
How many questions will be there?
Yes.
How many questions will be there?
How many questions? It's a 25 marks examination. So 10 MCQ questions will be there, and rest will be the short answer type questions, and it includes numerical problems also. So please solve simple numerical problems that we have solved during the class hours.
Okay, ma'am.
Only the simpler problems.
Ma'am, in MCQ, only solving we have to only show the answer or the solving also?
Better you show the solvings just beside the answers. You have to write only the options. You don't need to copy the statement of that option, like 1A, 2B, like that. But if possible, you please show the, if it's a numerical problems, then you need to show the, the solution just beside the option. If it is a
Yes, ma'am.
theoretical question, theoretical MCQ, then you don't need to write anything else. Clear?
Yes, ma'am. Yes, ma'am.
Oh, thank you.
Thank you.
Bye,
Thank
everybody.
you, ma'am.
Okay.
এখন আর কারো ক্লাস আছে নাকি?
स्वयं सर का क्लास है अभी।
Good morning, sir.
Good morning, sir.
Good morning, sir.
Good morning.
Good morning, sir.
Morning, sir.